Today we will learn about L'Hopital's rule. So now we've reached a stage in this course where we have learned about limits and we have learned about derivatives and we had the time to practice each of them. So now we will revisit limits. When we were computing limits, there were some forms that we often got that were not so clear what the answer was. Some of them are 0 over 0, infinity over infinity, infinity minus infinity, 0 times infinity, 1 to the power of infinity, 0 to the power of 0, and infinity to the power of 0. So these are what we call indeterminate forms. And of course, we have seen some techniques to solve limits when we have indeterminate forms. We have seen some techniques, especially for 0 over 0, where we would simplify, we would factor, rationalize, find a common denominator, and combine fractions. And we have seen some techniques for infinity over infinity and infinity minus infinity, where we would factor the largest power of x. So yeah, we have seen some techniques, but today we will learn the L'Hopital's rule, which helps us solve limits that come in these formats. So let's see what L'Hopital's rule states. Suppose f and g are differentiable and g prime of x is different from 0 on an open interval that contains a except possibly at a. Suppose the limit of f of x as x approaches a is equal to 0 and the limit of g of x as x approaches a is equal to 0, or that limit of f of x as x approaches a is positive or minus infinity, and the limit of g of x as x approaches a is equal to positive or negative infinity. This is just a complex way of saying that suppose if you plug in, you get a 0 over 0 or infinity over infinity. What do we do in this case? Then the limit of f of x divided by g of x as x approaches a is equal to the limit of f prime of x divided by g prime of x as x approaches a, if the limit on the right side exists or is infinity or negative infinity. Basically, what they are saying here is that if we plug in x equals to a and we get infinity over infinity, or if we get 0 over 0, what we can do is we can take the derivative of the numerator and the derivative of the denominator. Please keep in mind that we are taking the derivative of the numerator separately and then the denominator separately, and we are not doing the quotient rule. We will see an example in order to clarify this. So for now, let's start with an example related to 0 over 0 or infinity over infinity. So, limit of ln of x divided by x minus 1 as x approaches 1. First of all, as usual, we plug in. If we were to plug in x equals to 1, we would get ln of 1, which is 0, divided by 1 minus 1, which is 0. So in this case, we can use L'Hopital's rule. Make sure to write somewhere that you are using L'Hopital's rule. Check with your teacher to see which notation they prefer. So maybe write an H. Now that you have stated that you will use L'Hopital's rule, let's use it. So this is the limit. Now you take the derivative of the numerator and the derivative of the denominator. Again, we do not do a quotient rule. So this gives us the limit of The derivative of ln of x is 1 over x. The derivative of x minus 1, so the derivative of x is 1, minus 1 is a constant, so its derivative is 0. And again, this is the limit as x approaches 1. Now, this is equal to the limit of, so 1 divided by x divided by 1 is 1 divided by x. So this is equal to the limit, we can plug in 1 in this case. This gives us 1 over 1, which gives us an answer of 1. And I just wanted to mention that this example is from page 311 in the book. Now let's move on to another example. Let's compute the limit of e to the power of x divided by x squared as x approaches infinity. So as usual, let's start by plugging in. So if we plug in x approaches infinity, let's plug this in the numerator. So we get e to the power of infinity, which is infinity, and infinity squared is infinity. So we get infinity over infinity, which is a sign that we can use L'Hopital's rule. So let's write H for L'Hopital's rule. Now that we know we can use it, let's use it. We find the derivative of the numerator and the derivative of the denominator. So let's compute these derivatives. The derivative of e to the x is e to the x, and the derivative of x squared is 2x. So now again, let's plug in and see what we get. So if we plug in the numerator, we will get e to the power of infinity, which is infinity, and in the denominator we get 2 times infinity, which is infinity. So again, we get infinity over infinity, so we should use L'Hopital's rule again. So this gives us the limit of the derivative of the numerator divided by the derivative of the denominator as x approaches infinity. And now let's compute these derivatives. So the derivative of e to the x is e to the x, and the derivative of 2x is 2. And now again, let's plug in. So if we plug in the numerator, we would get e to the power of infinity, which is infinity, over 2, because we have a 2 in the denominator. So this is infinity. And we say that the limit diverges. And this also is from page 311 in the book. And now let us move to another indeterminate form, which is 0 times infinity. So this kind of limit is called an indeterminate form of type 0 times infinity. We can deal with it by writing the product f times g as a quotient. Fg equals to f divided by 1 over g, or Fg equals to g divided by 1 over f. This converts the given limit into an indeterminate form of type 0 over 0 or infinity over infinity, so that we can use L'Hopital's rule. So just a reminder or just a remark that we can only directly use L'Hopital's rule if we have 0 over 0 or infinity over infinity. So if we have any other indeterminate form, our goal is to make any other indeterminate form, our goal is to make it 0 over 0 or infinity over infinity. And how do we do that? So if we have multiplication of f times g, we can keep f in the numerator. However, we can move g to the denominator and do 1 over g. Technically, it is still the same thing because f divided by 1 over g is equal to f times g over 1, which is fg. So it's still the same thing, but in this way, we would have changed the limit from a limit that gives 0 times infinity to a limit that gives either 0 over 0 or infinity over infinity. So let's look at an example. The limit of x ln x as x approaches 0 from the right. So let us plug in. If we plug in, we get 0 times infinity. The x gives 0 and ln gives infinity. So we need to play around with this until we get 0 over 0 or infinity over infinity. So what we do is we move something to the denominator. It's gonna be either the x or the ln of x. Now you might ask, how do we choose? Let's say I will write both cases. If I keep the x in the numerator and move ln of x to the denominator, that's case 1. Case 2 is I move the x to the denominator and keep the ln in the numerator. The only way to choose is to look at both denominators, which are 1 over ln of x and 1 over x. Which one is easier to differentiate? Now I can tell you that 1 over x, it's very easy to find the derivative because 1 over x is basically x to the power of -1. You can just use the power rule in order to find the derivative. However, for 1 divided by ln of x, this will be a bit more complicated in order to find the derivative. This is why we stick with case 2 for this example. So always just check which term is easier to differentiate and send this one down to the denominator. So, as I said, ln stays in the numerator, x goes to the denominator, we get 1 over x in the denominator. And now again, let us plug in. When we plug in the numerator, ln of 0, we get negative infinity. However, the signs don't really matter, so you can put the negative, but it doesn't really matter in this case. So for L'Hopital's rule, whether it's negative infinity over infinity or infinity over negative infinity, you can still use L'Hopital's rule. And now 1 divided by x, let us plug in. This will give us infinity. This is a sign that we can use L'Hopital's rule. Let us use it. So let's find the derivative of ln of x. This will give 1 over x. And the derivative of 1 over x. This will give negative 1 over x squared. Let us simplify a bit. So this gives us 1 divided by x times x squared over negative 1, which simplifies to, we have x squared and x. So this simplifies to x, and don't forget that there is a negative 1. And now let's plug in 0, we get 0. And this is our answer. And this is from the book, page 313. So the limit of x ln of x as x approaches 0 from the right is equal to 0. And let us move on to another indeterminate form, infinity minus infinity. So if the limit of f of x as x approaches a equals to infinity, and the limit of g of x as x approaches a equals to infinity, then the limit of f of x minus g of x as x approaches a is called an indeterminate form of type infinity minus infinity. Again, there is a contest between f and g. Will there be an answer? Will the answer be infinity where f wins, or will it be negative infinity where g wins, or will they compromise on a finite number? To find out, we try to convert the difference into a quotient, for instance by using a common denominator or rationalization, or factoring out a common factor. so that we have an indeterminate form of type 0 over 0 or infinity over infinity. The summary of all of that is either combine the fractions or rationalize or factor or simplify in some form of way in order to change the infinity over infinity minus infinity into either 0 over 0 or infinity over infinity. Now, just a reminder, if this ever does not work with you, if you cannot seem to find how we are supposed to factor or rationalize or combine the fractions, don't forget that what we learned in earlier chapters is still true. You can still solve the limits the way we learned it before, and this would not be wrong. It will still give you the right answer. But let us still learn these different techniques so that whenever you're given a limit, you can have maybe more than one way to solve it and maybe to check your answer. So let's learn this technique. So let's start with an example. Limit of 1 over ln x minus 1 over x minus 1 as x approaches 1 from the right. So whenever you have like two fractions, it is quite clear that you are supposed to combine the fractions. So we need a common denominator, which would be ln x times x minus 1. So we multiply the first fraction in the numerator and the denominator by x minus 1, and the second fraction by ln of x in the numerator and the denominator. So this gives us x minus 1 minus ln of x in the numerator divided by ln of x times x minus 1 in the denominator. And let us plug in to see what we get. So initially this was infinity minus infinity. Let's see where we are right now. Now we have x minus 1 minus ln of x. So this is 1 minus 1, which is 0, minus ln of 1. So this is also 0. So in the numerator we get 0. In the denominator, ln of x, so ln of 1 gives 0, and 1 minus 1 also gives 0, so in the denominator we also have 0, and whenever we have 0 over 0, this means we can use L'Hopital's rule. So now that we can use L'Hopital's rule, let's take the derivative of the numerator and the denominator. Derivative of x is 1, derivative of negative 1 is 0 because negative 1 is a constant, and the derivative of ln of x is 1 over x. Now in the denominator we have a product, so let's use the product rule. So we leave the first term the same, we multiply it by the derivative of the second term, so derivative of x, as we said, is 1, minus the derivative of 1, and the derivative of 1 is 0. So this is 1 minus 0, which we can just write as 1. Now, then we take the derivative of ln of x, and we multiply it by the second term. So this is what we get. And now again, since we did L'Hopital's rule, let us plug in to see what we get. So in the numerator, 1 stays 1, so we get 1 minus 1 over 1, so 1 minus 1, which is 0 in the numerator. In the denominator, ln of 1 gives 0. 1 minus 1 over 1 also gives 0, so again we have a 0 in the denominator. So 0 over 0, this is a sign that we can use L'Hopital's rule a second time. Then again, we take the derivative of the numerator, so derivative of 1 is 1. And then we have a minus sign, we leave it outside. The derivative of 1 over x is negative 1 over x squared. All of that divided by the derivative of ln of x is 1 over x. And then we have x minus 1 divided by x. So we can do the quotient rule. So for the quotient rule, first of all, it's low d high minus high d low divided by the denominator squared. So we get x, we leave it the same, times the derivative of x minus 1, which is 1, so we get x, minus the numerator, which is x minus 1, times the derivative of the numerator, so times the derivative of x, which is 1. So overall in the numerator we get x minus, in parentheses, x minus 1, and in the denominator we get x squared. So let us simplify now. The limit of, in the numerator we have a negative and a negative, it becomes a positive 1 over x squared. Denominator we get 1 over x plus x minus x plus 1 over x squared. X minus x cancel out, so we get the limit of 1 over x squared divided by 1 over x plus 1 over x squared. So we might as well plug in right now to see what we get. So this gives us, let us plug in, so we get 1 over 1 divided by 1 over 1 plus 1 over 1 squared. So this becomes 1 divided by 1 plus 1, which is 1 over 2. And this is our answer. And we will now move to our last group of indeterminate forms, 1 to the power of infinity, 0 to the power of 0, and infinity to the power of 0. So, as usual, whenever we have a limit, we start by plugging in. So let's look at this example. So 1 plus sine of 4x all to the power of cotangent of x, the limit of all of that as x approaches 0 from the right. I just wanted to point out that all of these three indeterminate forms, we deal with them in the same way. So in this example, x is approaching 0 from the right. We would like to plug in. So sine of 0 is 0, 1 plus 0 is 1, and the cotangent of x, cotangent is cosine over sine. Cosine is approaching 1 because cosine of 0 is 1, and sine is approaching 0 because sine of 0 is 0. So we have 1 over 0, which would be approaching infinity. Therefore, here our entire 1 plus sine of 4x all to the power of cotangent of x, if we were to plug in, we get 1 to the power of infinity. This is an indeterminate form. So what do we do in this case? What we do is everything that's inside the limit. So all of this, we make this, let's say, let y be equal to this. It does not have to be y. It has like it can be any variable. But for now, we will use y. Let y be equal to all of that, as I wrote in here. What happens is we take the ln of y. So ln of y equals to the ln of 1 plus sine of 4x all to the power of cotangent of x. We can use log rules, and cotangent, we can now drop the power and write it right here. So we get cotangent of x times ln of 1 plus sine 4x. Just keep this as a reminder that cotangent of x is 1 divided by tangent of x. I'm saying this just because whenever we're computing limits or so whenever we're computing anything in math, actually, it's much simpler if we were able to simplify what we have. So if we have cotangent of x times ln of 1 plus sine of 4x, we can simplify this. We can write the cotangent in the denominator. So if I were to move the cotangent to the denominator, it becomes 1 divided by cotangent of x, and 1 divided by cotangent is tangent. Again, this is just for the sake of simplification because this makes it easier to compute the limit. If you don't do this now and do this at a later stage, it will still be okay. So now let's compute the limit of ln of y. You might ask why are we computing the limit of ln of y, whereas the actual limit we would like to compute is y. So first we'll start by computing the limit of ln of y, and then we will use it to find the limit of y. So the limit of ln of y as x approaches 0 from the right is the limit of ln of 1 plus sine of 4x divided by tan x as x approaches 0 from the right. And here, let us plug in to see what we have right now. So the sine of 4x is equal to sine of 0 in our case because x is approaching 0. So sine of 0 is 0. 1 plus 0 is 1, and ln of 1 is 0. So in the numerator, we have 0. In the denominator, tan of 0 is 0. And now we have gotten 0 over 0. This is a sign that we can use L'Hopital's rule. Let us use L'Hopital's rule and find the derivative of the numerator and the derivative of the denominator. So in the numerator, we have ln of 1 plus sine of 4x. This is the chain rule. First, we find the derivative of what's outside, so the derivative of ln is 1 over x. We compute it at 1 plus sine of 4x. This means now we got 1 divided by 1 plus sine of 4x, and then we multiply it by the derivative of what's inside the ln. So we multiply this by the derivative of 1 plus sine of 4x, and we get derivative of 1 is 0, derivative of sine of 4x, again a chain rule. So the derivative of sine is cosine, we compute it at 4x, and we multiply it by the derivative of 4x, which is 4. Now let's move to the denominator, derivative of tan of x. We learned this is secant squared of x. So we can now plug in to see what we get. We get in the numerator 4 cosine of 0 divided by 1 plus sine of 0, all of that divided by secant squared of 0. So cosine of 0 is 1, sine of 0 is 0, secant squared of 0 is 1. Overall, we get 4 divided by 1, all divided by 1, which is 4. Now again, this is what we get for the limit of ln of y as x approaches 0 from the right. Now we would like to find what is y. Y is equal to e to the power of ln of y. So if I would like to find the limit of y, this is equal to the limit of e to the power of ln of y as x approaches 0 from the right. Now I can write the limit in the numerator, so I get e to the power of the limit of ln of y as x approaches 0 from the right. And we already found that this, what I highlighted right now, we already calculated it and it is equal to 4. So our final answer is e to the power of 4. And let us now look at another example to help us understand. So limit of x to the power of x as x approaches 0 from the right. Again, let us plug in, we would get 0 to the power of 0. So everything that's inside the limit, so x to the power of x, we will make y equals to x to the power of x. Therefore, ln of y is equal to ln of x. Now we can use log rules, and we can drop the power down, so we get ln of y equals to x ln of x. Let's find the limit. The limit of ln of y as x approaches 0 from the right is equal to the limit of x ln of x as x approaches 0 from the right. And let us look back. We actually have computed this limit in a previous exercise right here, where we said that the limit of x ln of x as x approaches 0 from the right is in fact equal to 0. So again, it's really helpful. We can always use what we have, limits we have computed before. So let us write this. This is equal to 0. And again, this was the limit of ln of y. Let us find what is y. Y is e to the power of ln of y. So the limit of y as x approaches 0 from the right is equal to the limit of e to the power of ln of y as x approaches 0 from the right, which is equal to e to the power of limit of ln of y as x approaches 0 from the right, which is e to the power of 0, which gives us 1. And this is our answer.